This is a video on implicit differentiation. I wanted to make this video to be a little more explicit at how the process starts. There's lots of other examples in the textbook and videos that are provided that are great. They're fine. They show the whole process, except none of them, I feel, really do a good job of explaining the initial setup. So what I want to do here is take the derivative of y with respect to x. Now, what we're asked to find, dy dx, implies that y is the output variable and x is the input variable. And yet, the relation that is not written as the output variable, the input variable. So, and in fact, in this case, it can't be solved for y. There are other equations that you'll do in this section that you technically could maybe solve for y and find the derivative in a more traditional technique. But we can't do that here, and we can't do that for many of them, most of the ones that you'll see here, because we just can't solve for y by itself, and so we have to do something different. So here's what we do. We take the derivative of both sides with respect to x. So we get this. We have the derivative with respect to x of the entire left side. And then we have the derivative with respect to x of the entire right side. So of course, what we're doing here is we're balancing the equation, right? We're doing the same side of the equation as we're doing to the right side. Okay, great. It's important to remember that this is what we call an operator. We are doing something to this expression, kind of like taking a function or taking a natural log or taking a square root or taking a sine, right? We're taking a derivative with respect to x of this thing. Okay, well, to do that, of course, we know this is a sum, so the left side, that becomes the derivative of x squared plus the derivative of y cubed. And on the right side, it becomes the derivative of 4x minus the derivative of y. So that part's fairly straightforward. And then we keep going. We say, okay, well, I can do this one. That's easy. That's just 2x. No problem there. This one's a problem, right? Because we're asked to find the derivative with respect to x of y cubed. And well, I can't do that, right? Because y is the variable. Now, in some situations, if I just said, what's the derivative of k with respect to x, you'd say, because k is a constant. Or what's the derivative of c with respect to x? It's 0. What's the derivative of 5 with respect to x, right? If we're taking the derivative of something that's a constant, the derivative is 0. But y cubed is not a constant. We know it's not a constant because we're explicitly told to read it, no pun intended there, explicitly told to treat it as the output variable in this implicit function, this implicit relation, right? It's implicit that y is the output variable and x is the input variable. And so we're told to treat y as if it's a variable. That means this is not a constant expression, so its derivative can't be 0, or at least probably isn't 0. I guess it could coincidentally turn out to be that. But no, this is a variable expression. So since we can't take the derivative of y cubed with respect to x, we have to change our perspective, as we've done many times in this course. Right, I can't deal with this expression as it's written, but I could take the derivative of that expression if I was taking it with respect to y. Well, that's something I can do. Right, I can take the derivative of y cubed with respect to y. That's just 3y squared. Again, for that, you're going to just ignore everything else on here. You're going to ignore this, ignore that, ignore this, ignore everything, and just say, okay, forget about all the x's. What is the derivative of y cubed with respect to y? That I can do. It's 3y squared. The problem is there was other stuff. I changed it. And if I'm going to change the variable differentiation, this is no longer the same expression as that. So I have to reconcile that. And the way we reconcile that change of variable is with the chain rule, essentially. So let's see how that works. I have to multiply by the derivative of y. There we go. The derivative of y with respect to x. Now that might feel a little weird. It's really an application of the chain rule, right? Maybe not an obvious application of the chain rule, but that's really what it's based on. Now let's look at this for just a second, right? algebraically, if I treated this as fractions, if I treated this as, dy cubed on top and dy on a bottom, and then over here, dy on top and dx on the bottom, I could say, oh, let's cross those dy's out. If I could do that, which we technically can't, right? But for the sake of understanding it, it works. We sort of can. We can think of it that way theoretically. If these were actual numbers, I could cancel out those things. dy on top, dy on the bottom. And now this expression is algebraically saying the same thing as that, right? So that kind of helps us see that, oh yeah, that's a legal change of variable, right? That is a legal change of variable. I'm allowed to do that. Okay, now of course I don't want to cancel out those dy's, but it can help us if we write it out that way. And this is the part that the book and the videos kind of skip over, and I think not everybody needs this, and that's great. And in the long run, you shouldn't have to write it out this explicitly. But I think starting out, this helps a lot of students to write it out that way with that change of variable. It can help you see, oh yeah, okay, this really is the same as this is what I wanted, but this thing really is the same because algebraically the dy's cancel out. Okay, so now hopefully we see that, yeah, those things are the same, but I don't want to cancel out those dy's. Okay, well, let's keep going to the right side of the equation, and then we'll see how that simplifies. So the right side, fairly straightforward. We got the derivative with respect to x of 4x is just 4. And notice this one over here, that might feel weird, but what this one over here says is take the derivative of y with respect to x. Well, that's my objective, right? I'm trying to find dy dx. I found it, right? It's right there. It's also over here, but okay. So that might feel like a trick, like it's a trap, like we hit a dead end or something, that this is an unsolvable thing because we're asked to find this thing and we found it. But we got to realize that, okay, after this, I'm eventually going to end up with an equation that I'm actually going to solve for dy dx. So I actually need the expression dy dx to show up at least once in my equation. Now it actually showed up twice here, once there and once there, but that's okay. All right, so let's keep going. On the left side, of course, 2x was 2x, and then I was taking the derivative with respect to y of y cubed. Well, that's 3y squared, as I said before. Now that's being multiplied by dy dx. Nothing's changed there. And again, I do not know what the expression is for dy dx. I'm not supposed to. That is the objective. So I'm not supposed to know what dy dx is yet. I'm trying to find what it's equal to. Okay, I didn't have anything to simplify on the right side just yet, so there we go. Now I want to point out right now that calculus is done. I've evaluated all the derivatives that I can, right? I do still have a derivative of y with respect to x that I haven't evaluated, but I can't evaluate that. I just have to solve for it. So the rest of this is actually algebra, solving for dy dx. Okay, so I'm going to balance equations again. I'm going to get all my dy dx terms on the right, on one side, and all of my non-dy dx terms on the other side. So I'm going to get this 3y squared times dy dx and this dy dx on one side of the equation, and I'm going to get this 2x and this 4 on the other side of the equation. So a little bit of balancing equations there, and we get this. We get 3y squared times dy dx plus dy dx, because I added this one to both sides. That's why that's a plus there. And on the other side of the equation, I have 4 minus 2x, because this 4 was over there on the right side, and I subtracted this 2x. That's why that's a minus there. Okay? So now I've gotten all my dy dx terms on one side, and now I'm going to factor that dy dx. Factor out a GCF on the left side. And then I just divide both sides by 3y squared plus 1, and I'm done. That is the entire problem, right? So I have found dy dx. I got it by itself. These problems are a little bit harder to check than some of the other problems, but one thing you can do if you are using a graphing calculator where you could graph this equation, which desmos.com/calculator, you can type that in and graph it, and it gives you a curve. And so on. And so you could, and some of the problems will ask you to find tangent lines, and that's something you could graph the curve and graph your tangent line and see, oh, it really is tangent line. But for this problem, they didn't ask us to find a tangent line. They didn't ask us to evaluate dy dx. They just said, what is dy dx? And so that's the whole problem. So again, this video, I just wanted to be a little more explicit as to really what's happening, because all the other textbook and the videos, they just kind of from here to here, and I felt like they're kind of missing that how step. All right, so one more time. We want to take the derivative of y cubed with respect to x, but we can't. What we can do instead is take the derivative of y cubed with respect to y. But if you change that variable differentiation, you have to reconcile that with the chain rule. And so I multiply by dy dx. I'm allowed to do that because, again, if I did some algebra to cross the off, I would get this thing, which is equivalent to what I had right above it. I don't want to cross off the dy's, but that lets me see that it is algebraically equivalent. And then I say, okay, fine. Now I can take the derivative of y cubed with respect to y. Forget the x's, just the whole variable is y. And there you go. All right, so you got other videos, other examples in the book and in my notes and stuff like that you can take a look at. And you can have all sorts of fun with differentiation now.